So my name is Nada Golmie, and I'm from the Communications Technology Laboratory at NIST. It's a U.S. Laboratory in the U.S. Department of Commerce. So thank you for the invite to speak to you today about an effort that we undertook about a couple years ago now. And it was mainly to capture was the big areas of that would warrant additional research, additional investments. And it is not unlike other roadmaps and various projects and visions. We didn't really attempt here to project a vision. We did not. So this is not a roadmap where we, as you all know, in a roadmap, you start with a current state of the art, and then you have a vision, you describe it, and you basically have to explain how you go from today or from a point in time to a vision. And then you say, here's how we're going to get there. This is not that process. This basically says no matter what vision you subscribe to or whatever you want, wherever you want to go, here are some big areas that would benefit from additional R&D. And this would be good for researchers trying to look for topics and problems. It would be good for funding agencies that are looking to spend any invest in areas. So that's the main intent, the background for this. And we partnered with the National Science Foundation in the US. So it's the NIST and National Science Foundation. We also had collaborators and people we worked with throughout industry. Worldwide, I would say, we didn't really focus on a region, the US. We just tried to speak to many researchers. Some of them are participating in your project. And to have the sort of, because we believe that these problems are fundamental and they're not based on geographic areas. So basically, my main point today is to point you to this report, which is pretty much self-explanatory. I'll go through some highlights here today, and hopefully it can answer some questions. I'll be happy to do that. The process was we had a number of one-on-one conversations with like a dozen people, visionaries in the industry, and to get us started, to get us grounded. Where did the people feel like were the big areas, the topics that they identified? And based on this preliminary input, we send out open-ended questionnaires and to gather feedback from the community. And this was an open process. It wasn't just we're talking to our friends and colleagues, but we tried to make it as open as possible so anyone could actually sign up and be part of the working group. And then we had several conversations, webinars, where we actually discussed each topic in more details, and either via a sort of a conversation, or it was a panel where we had a number of folks who described different problems or issues, and then we had a conversation on that. And then we basically took that input. So I don't take credit for this material. I just was mostly with my colleagues taking notes and making sense out of this in terms of organizing it, right? Because sometimes the ideas were scattered and we needed to come together and make some sense out of it. So here's what bubbled up in terms of the main topics, right? And these are the usual sort of suspects in terms of hardware, higher frequency research. I know the golden bands, the golden frequencies are in the sort of the lower sub-6, which is a great spectrum to operate in, but we also recognize that, and the community recognizes that we probably need to continue to work on the higher frequencies and address some of the issues there. And then spectrum sharing, spectrum science, joint communication and sensing as a great application and capability that is being considered for NextG. Obviously, there's no respectable report talking about wireless communications that doesn't mention AI and ML. And also the data issues and the data that needs to, because we can't do AI and ML without having data. And with data, you have privacy, security, and stuff like that. The also recognizing that it's not just going to be traditional cellular or Wi-Fi systems, but also incorporating non-terrestrial networks in order to really have this integration of the various networks. And of course, last but not least is sustainability and energy efficiency. And obviously, we did not, for example, address quantum, post-quantum. We didn't address cybersecurity and security per se, and those are very important. But we feel that there are communities that are working in them, and we wouldn't be doing them justice if we just address them tangentially. We point to things, but we believe that there are also other communities that are working in areas that are very important to this. So a little bit more on some of these sort of high-level areas. This is where the main buckets, if you will, of the various issues, the gaps. By assuming big list of issues, we try to group them together wherever it makes sense. Obviously, we think that there is a lot to be done in terms of higher frequencies, making higher frequencies useful. Also from a hardware development and innovation, a lot of room for improvement in terms of also the measurement needs there and the modeling, but also in terms of the deployment for network capacity and coverage. How do we, in the recent years, we've heard a lot about large intelligent surfaces and tunable surfaces and tunable programmable antennas. So there's more work that needs to be done there. In addition to that, in conjunction with that, there's all the protocols and the architectures that need to be also developed. It's not sufficient to just develop a piece of hardware or an antenna, and then we have to say how it's going to be combined with the rest of the system. In terms of the other big area is spectrum, and of course, as wireless communications, for us, we need more always spectrum. We need to also, because spectrum is a finite resource, we need to look at better ways of sharing. We've been talking about sharing for many years, for decades now, but obviously the technology is, a lot of it is there, it is available. How do we put it in practice? How do we deploy it at scale? Of course, there is sometimes technology is there, but people don't trust it or don't want to necessarily give up spectrum allocation because that's what they're used to. That's what they have customers that depend on that, and that's how the operation has been. But there's a lot that's been happening. And today, for example, we think that spectrum sharing is part of 5G, NextG, 6G, and it should be native to any development. So we're not looking at just developing in a particular band, but we're also looking at how do we better share bands, how do we also work on multiple bands. Oftentimes, we look at mostly for propagation, we look at just models for coverage. So we're looking at computing link budget, but we need to pay attention to interference models. How do we better characterize interference models so that we could do more efficient sharing? In terms of one application on one space that has been receiving a lot of attention recently is this joint communications and sensing. Obviously, we've been doing sensing for a long time. There's been sort of radar applications for also decades. And then we have the communication infrastructure that is there. Question is, can we utilize the communication infrastructure in order to do sensing, in order to get more information, mainly about the environment, right? Because a lot of the applications, a lot of the use cases that we foresee for the future are basically about being able to position the environment, understand better the environment in order to have a more efficient network and communication system, but also to do other things, like the metaverse, like the AR, VR, etc. So for a lot of this is, can we take advantage of the signals that are, being communicated? And there is a bit of realization that yes, maybe we don't have to deploy a sensor network that is completely separate, and then we can take advantage of what is being communicated, the signals, in order to also understand the environment. So that's going from there. But however, we also realize that can we get 2 for 1 and maybe, but then how do we make sure that the protocols and the technology is there in order to incorporate this additional information and take advantage of what is there? A lot of groups already are taking this into account, whether it's the Wi-Fi systems. I think people have been doing some sensing already with just Wi-Fi signals. There's new development standards to include the sensing. 802.11bf, for example, is focused on the sensing aspect. Also, the 3GPP side, also there's sensing, looking at sensing for the next releases. A lot needs to happen in order for this to be completely developed from the standard point of view and from in order to enable deployment. Of course, AI ML, I think we can see both the need of AI and ML for wireless communications, given the complexity of the systems and the communication systems. And also we can see that wireless communications are a key enabler for AI and ML. So it's both ways, AI for wireless and wireless for AI. And also, as we, again, deal with a lot of data, process a lot of data, we need to have maybe the AI and ML be efficiently developed and maybe improved in order to do a lot of things, perhaps at the edge or much closer to the edge, as opposed to just collecting a lot of data from everywhere and then processing it and then in the cloud and then getting back the insights. So we're looking more at AI, ML at the edge, this edge computing concept, and also where the radio is also a computer that is able not only to connect and communicate, send the signal, but also to process a lot of the information so that it is able to adapt the communications and the system. Again, AI native, we've heard that for NextG and going forward, and I think this is more has to happen also in order to include that for the different functionalities and the building blocks. When we talk about AI ML, data is basically where it's the sort of the gold or the fuel for the AI and ML, and we need to have data being available for doing this information to gather information about whether it's an environment, adapt the systems, and then of course how do we treat the data. It has to be available, it has to be used, but also are we talking about how do we maintain the privacy and security of the data. There are some concepts and some frameworks that people have suggested, including NIST, to maintain trust and confidence in the data. But a lot of work needs to happen there in terms of how do we ensure that the data is available for use, but yet it is protected and privacy is maintained. In terms of, okay, we're talking about a very complex system, complex communications and integrated system. So we also need to think about, does this architecture that has served us so well now, is this it, or do we need to also make improvements and upgrades to the network architecture? So looking at going forward, and what are the architectures that are going to be more flexible to allow us for doing things very cost effectively, but also integrating different devices, different services, and different systems and technologies, going from things that are not controlled by a central system, more on the D2D, device-to-device communications, the M2M, with the proliferation of IoT devices, and then also considering this open radio access architecture, which allows us to do a lot of plug and play and to look at things into very distributed, where we can implement things in a very distributed fashion. So things to consider in terms of evolving the network architecture. I spoke about the integration of different networks and services. Of course, the appeal for non-terrestrial networks, for especially for large coverage areas or areas where deployment of a more traditional cellular system is not cost effective, and there's a lot of appeal for things like that. And when we think about that, it's just not just okay, here's a non-terrestrial network. I think this is where we have to overcome some of the challenges with respect to the large round trip time, with respect to how do we make sure that the information that is collected, that is being made available, that is integrated. So a lot of interesting area for research in terms of the non-terrestrial. Of course, standards need to be developed to ensure that is part of it, and they are being considered and revised for that. Last but not least is the sustainable and energy efficient network. It is put here as at the end, not because it's an afterthought. It should be really at the heart of it. And I think many years ago, people were conscious of the fact that they needed to look into this, but the models or the information about the energy consumption and the footprint was very rudimentary. Today, we can do a lot more in terms of better understanding the energy consumption, better understanding the and developers that are more efficient, and technology that is more efficient. However, a lot more needs to happen, and from radios that are always on to things to operation of cellular systems that are. I think there's a lot to be done in that context, and our community recognizes the opportunity to make major improvements in that area. I think with time, I'm going to stop here, and happy to answer questions.